to finish up our little overview of classical optics, we're going to talk about total internal reflection and dispersion before we get into some more advanced cases of how we're going to apply the ideas of reflection and refraction. So for total internal reflection, we know that mathematically the sine of an angle always has to be between two values. The lowest it could possibly be is -1. The highest it could possibly be is +1. So that means for certain values of index of refraction and some angle of incidence, then Snell's law actually doesn't give us any solutions for theta 2. It's mathematically impossible. So let's say we have glass for medium 1, and for medium 2 we'll have air. And our angle of incidence is 87 degrees as it goes from the glass to the air. So the angle of refraction then will be given by sine theta 2, the angle of refraction there, equals 1.6. So when you set up that ratio and sine of that angle, you get sine of something is 1.6. And we know mathematically there can't be any solution for that. So while the mathematicians are still working on some kind of explanation for why these things happen this way, the physicists just kind of say, okay, whatever, I guess that happened because we saw it happen. It's supported by observation. So when that happens, this phenomenon is known as total internal reflection. So for those two given media, the glass and the air in our example, we have what's called a critical angle. Critical angle is theta c, and it's just defined as the smallest angle of incidence for which total internal reflection occurs. So we've just barely broken that sine theta 2 equals some number that's a little bit above 1. So from Snell's law, if we're looking only at everything in terms of variables, that we know sine of your angle of refraction is equal to n1 sine theta 1 over n2. So refraction is only going to occur, so only occurs if, whoop, my subscripts didn't go through right. So n1 sine theta 1 over n2. So we'll only have refraction if all of this stuff is less than or equal to 1. It can't be any bigger or else we can't do the inverse sign. So if we set the left side equal to 1, the very uppermost limit, then we can figure out an expression for the critical angle. So if we say this is equal to 1, then we would have, alright, so it's just the same equation that we had up above, but you can see now I changed the subscript on the theta to a c instead of a 1 because this is the critical angle that we're going to try to come up with an expression for. So just rearrange the whole equation, solve for theta. So multiply by n2, divide by n1, take an inverse sign. So we'll get theta c has to be equal to inverse sine of n2 divided by n1. So just keep in mind when you're using this equation, n1 is the medium that it's already in. The light is already in here. It's trying to leave 1 and transfer into 2, but it doesn't quite make it. Alright, so let's try it out in an example. I'm going to copy it real quick so we have it later on. Alright, index of refraction for water is 1.3, and for air, it's essentially 1.0. What is the maximum angle of incidence at which a ray of light can pass from water into air? So this question is asking us to find the critical angle for the transfer from water to air. So here's our equation with the subscripts all messed up. Down. Alright, so let's plug in the stuff that we know we want to do. Theta C is going to be equal to inverse sine of N2, the medium that it's trying to enter, so into air, divided by the medium it's coming from, which is water, so 1.3. Alright, so we go through, plug all that in the calculator. You should be seeing 50.3 degrees would be just that angle where it starts to totally reflect. So anything up to 50.3 and the light will be able to pass through. So for dispersion, there's one little thing about the way light behaves when it's refracted that we haven't considered so far, and that's that the index of refraction depends a little bit on the wavelength of the incident light. So if you have a mixture of a whole bunch of different waves, and they're all different wavelength, and they're refracting, then each color or each different wavelength is going to refract a little bit differently. And we'd say that they disperse, they spread out. So in general, when you have light that's a longer wavelength and a lower frequency, it's going to refract less than light of a shorter wavelength and higher frequency. So if we're trying to talk about the refraction of violet light, it should be greater than the refraction of, say, red light. So dispersion is actually what explains why we're able to see things like rainbows, or if light shines through a glass prism, it breaks into kind of that rainbow pattern. So the white light that comes from the sun, it's a mixture of a whole bunch of different colors of light, a really, really big range. So when the white light passes through water droplets in the air, they kind of have a lensing effect, and the different wavelengths, since they're traveling from air into water and then back out again, they get refracted differently. So the violet light gets refracted at a steeper angle than the red light. So violet light that reaches our eyes seems like it's coming from a little bit higher than the red light did, even though they're coming from the same ray. So because every color is refracted at a slightly different angle, then they kind of arrange themselves at different heights, all one on top of each other. So the colors of the rainbow that you learned, that's kind of the order that they get refracted in. Not kind of. Why'd I say kind of? That's exactly the order they get refracted in. Alright, so we'll start next week into optical instruments, where we start talking about these ideas a little more mathematically, rather than kind of conceptually like we have been this week.